major topics today, and that is going to be these three down at the bottom, or those are going to be. We're going to talk about some properties, we're going to talk about transformations, and we're going to talk about proofs, because I know that's always something we have a lot of questions on. Other things I will talk about tomorrow, so if you want to come back tomorrow, we'll plan to do this again, or you can just watch it later. So generally, most of your teachers, I'm sure, have gone over the format with you, but your test is at 12:15 on Tuesday, and it is 10 multiple choice where you will get no partial credit. There are 7 short answers, including 1 construction, and there are 2 proofs. So there will be a similarity proof and a congruence proof. Make sure you know your quad properties. Those are going to be in there. And a couple tips before we get too far into actual content. But number 1, make sure you're reading questions carefully, right? A question might give you something and you might need to solve for X, but it might not just ask you to solve for X. So make sure you're reading and saying, do I need to plug it back in? Did I actually answer the question? The second thing would be make sure you're explaining why if you're asked to. So some questions might ask you for an answer and then ask why. And we really are looking at how thorough your responses are there. So please make sure that you're thorough and really explaining as best you can. I had a question about when the test gets over. So you're required to stay for a minimum of an hour. And I think that you have 90 full minutes. So you'll have an hour and a half if you need it, but you have to stay for an hour. Please bring ruler, compass, calculator, pencil. Those will be important. Your reference sheets, if your teacher collected them, then you will get back at the test, so don't worry about bringing those. And otherwise, just come prepared and make sure you've studied. Get a good night's sleep, eat breakfast. All of those are important, okay? All right, so let's get into some content. So, topic number 1 we're going to go through are different properties of segments and angles. And the first one that I want to talk about are parallel lines, because these come up all the time, and sometimes, even though we know properties of parallel lines, the way questions get worded can be weird for us. So on this, we're going to look through this. This is an actual Regents question, and we've got these segments as shown, and it says, which statement would allow Steve to prove that those lines are parallel? And so what I want you guys to think about is, we are trying to show the lines are parallel. What you need to think about is lines are parallel when certain properties are true. And all of those angle pairs that you've learned about this year, those are really the properties. So we know that alternate interior angles exist. Well, lines are parallel if those alternate interior angles are congruent. We know that corresponding angles exist. Lines are parallel if corresponding angles are congruent. So what I want to do is I want to look through each of these options in my pairs and see which angle pair they give me. So let's start with the first one, CFG and FCB. So CFG, I'm just going to follow my line, CFG, that's this angle. And FCB, so FCB is that angle. So this would be this pair of angles. And look at the shape I just drew. So FCB was this, and CFG was this. And so you see there that I have like a Z, right? That Z tells me that those are alternate interior angles. And if alternate interior angles are congruent, that does mean my lines are parallel. So that's important. So let's look at some other ones and see why those are wrong. So the first, or option 2, AFB and BFC. So, I'm sorry, ABF. ABF is this one, and BFC is this one. So that's saying here, I'm just going to do this again, that this angle, ABF, is congruent to this angle, BFC. Now, that is not one of the angle pairs that I learned about this year. That's not alternate interior. That's not corresponding. Those are just 2 angles that happen to be in the same diagram. So that's not going to be any of my angle pairs. The next one I see is EFB and CFB. So EFB is this one right here. And CFB is this one that we just talked about before. Those are adjacent angles. They're next to each other, but other than being adjacent, there's not much that I see going on there. So yes, those are adjacent, but they're not one of my angle pairs that makes lines parallel. And last, CBF. So CBF is this one, and GFC, that is this one. And so these are interesting because Some people will look at that and say, oh, they're both interior. They're on alternate sides of a line, but they don't make that Z pattern, right? And so those are not alternate interior angles. So those are a few reasons that some of those would be wrong. So remember, you're looking for your angle pairs. Answer choice 1 gave me that Z. These are in like my armpits of the Z, right? And so those are my angle pairs. Okay. Again, if you have questions, just send them as we're going. So let's look at this next one. In this diagram, EF intersects AB, and GI is drawn so that GH is congruent to IH. So I'm going to label that GH congruent to IH. And that signals something very important in my brain, because when I see two congruent sides, the first thing that, especially hopefully if you're in my class, you're thinking is, well, that means in this triangle there are two congruent angles. So I'm going to look at the angles across from those congruent sides, and those are going to have to be congruent, because in an isosceles triangle, your base angles are congruent. So I already know that, and I know nothing else. They tell me that EGB is 50, so I'm going to label that. I've used that info. And DIG is 115. DIG is 115. And they want to know why those lines are parallel. And this is where, when I said before, make sure you're explaining, make sure that you really are. You're looking at it and saying, why is this true? So let's start to figure out whatever we can. I'm going to first look at this and say, okay, right here, I see a linear pair. Okay, I see a linear pair there. So this one over here is 115. I'm going to do 180 minus 115. And that tells me that this angle right here is 65. So that's a start. Now, based on what I know, this angle right here would also be 65, because in my isosceles triangle, base angles are congruent. And now, here's where you can really stop and think. I see here, let me change my color, a triangle, and I know that the angle sum of any triangle is 180 degrees. So I know that these two base angles are each 65. So I'm going to figure out this angle right here, angle GHI. So that would be 65 plus 65 plus some number equals 180. 65 plus 65 is 130. So that's 130 plus x equals 180. And subtract 130 from both sides, so x equals 50 degrees. So I see here now that this is 50 degrees. And I get excited, because what I notice now is that I have this pair, and again, I'm just erasing these so I can highlight something else for you guys. I see that I have a pair here that are both 50, okay? And when I look at those, I notice that those two angles are on the same side of that transversal, and they're both above the line. So if I looked at my parallel lines, those are right here and right here. Sorry, I can't see that. So that's a pair of corresponding angles. Okay, those are corresponding angles. And we know that if corresponding angles are congruent, then the two lines have to be parallel. So what I could do here is say, okay, great. Now I know a theorem, once I've shown all this work, that says if corresponding angles are congruent, right? If corresponding angles are congruent, that means that the lines must be parallel to each other. And we could say that in much more technical terms. We could say when two lines are cut by a transversal with corresponding angles congruent, lines must be parallel to each other. But that's what you would want to explain. You would want to show your work so I could see how you got those numbers, and then explain that this angle and this angle are corresponding, and corresponding angles are congruent. Now, I did see one question as I was working, so let me just make sure that I hit that. So one question was, how do you know to look for that 180? Good. So what I'm looking for there is always going to be a triangle, right? I know to add these up and subtract from 180 because these three sides make a triangle, and that is going to have an angle sum of 180. So that's how I knew that there. Okay. Again, continue to send questions as you guys have them. The next one I'm going to look at is related, and this ties right into a question that I just got. How do you know what the base angles are? So we're going to look at this because this is an isosceles triangle question. So right here, I see that I have an isosceles triangle. And the reason that I know I have an isosceles triangle is not because the sides are right. The reason that I know is actually because the base angles are marked. And so I see that I have these two angles, and those base angles are congruent, which means the sides opposite them are congruent. So on this, what I can say is that this side is going to have to be equal to this side. So I could say, okay, 2x plus 6 is going to have to equal 3x minus 6, and then solve for x. And I knew that again because my base angles were congruent, so the sides across from them are congruent because it's an isosceles triangle. So set those equal. I'm going to subtract 2x over and add 6 to the other side, so I get x equals 12. Now, often what you'll see on a question like this is not just solve for x, but you'll also see something like, what is the measure of VT? So if I wanted that, then I would say, okay, VT equals 3x minus 6. I know that x is 12, so it would be 3 times 12 minus 6. So that would be 36 minus 6, which is 30. Okay, one more isosceles one we're going to take a look at, and that's this one right here. And some of my classes, we got to this question in class, some we didn't. So if you've seen it before, trust me, everything else in this review is new, but some of my classes didn't get to this, so I wanted to make sure we talked about it. So on this one, I see this as isosceles because I have these two sides marked equal, or marked congruent. So I know it's isosceles. Two equal sides makes me think two equal angles. So I'm going to start with the only angle I know, which is this 125 right here. And I don't see anything else that I totally know, but I do see that that 125 and that x make a linear pair. They make a straight line, right? So those have to add up to be 180. So there, I'm going to do 180 minus 125, which would equal 55. And so I know x degrees is really 55 degrees. And then here's the key. I know that I have congruent sides, so the angles across from those sides will also be congruent base angles. So if that side is 55, so will this be. Now, keep thinking, okay, these make a linear pair. So if that's 55, this is 125. And then again, look and see, oh, this is a triangle. Angle sum in any triangle that we know of is going to be 180 degrees. So I can add up those two angles, 55 plus y has to equal 180. This is 110 plus y equals 180. And so then I would get y equals 70 degrees. So that would be one way to solve for it. So when you're looking for missing angles, the thing I would caution you guys to look for are three things, really. Two we really worked with a lot here. But first thing I would caution you to look for are linear pairs, right? Look for linear pairs. Those are going to look like two angles that form a straight angle, right, together. And those are supplementary. They add to be 180. The next thing I would tell you to look for would be vertical angles, which we did not use a lot here. But vertical angles would look like this, and they would be across from each other. We could have used them in this problem up here. We could have said that, oh, this top angle was 50, so this vertical angle would also be 50 because those are across from each other. And then said that these two would be alternate interior. And the last thing I would have you guys look for is it an isosceles triangle in any way? If you know that you have base angles congruent, then sides must be, and vice versa. Okay? All right, send questions if you have them. The last thing we're going to look at with these, and then we're going to do a lot with transformations tonight, are triangle medians, or we've also called them triangle midsegments. And remember with these that we have two bases, these are trapezoids, not triangles. We have two bases, and those bases are going to be parallel because it's a trapezoid. So that's always how you can find them. This segment right here in the middle is going to connect the midpoints of these two sides. So those two pieces should be congruent, and so should those. And when we think about middle in math, a lot of times we think about average. So what I want you guys to think about is that this median, or this mid segment, is going to be the average of your two bases. And when you hear average, think add up and divide by 2. So, to average these, I'm going to take my two bases and add them. 2x minus 1 plus 7x plus 3. And I'm going to divide that by 2. So adding up, divide by 2 because it's an average again. That's going to equal the length of my mid-segment here, which is 19. So now I need to solve this. And there's more than one way to do this, but the way that I typically do is I'll start by combining my like terms in my numerator. So 2x plus 7x would give me 9x. Minus 1 plus 3 would give me plus 2. Divided by 2 equals 19. I have some students who here like to divide both sides by 2 here. They use the Miss Blakely trick, right? Divide this by 2 and divide that by 2 because you love dividing. But I don't always do it that way, so I'll show you the other way I do it, which is to say I'm dividing by 2. So I'm going to do the inverse operation to that, which would be to multiply by 2. And whatever I do to one side, I do to the other. On the left side, those 2's will undo each other. They will cancel. So I will just be left with 9x plus 2. On the right side, I have 19 plus 2, which is 38. And so what I wind up with is 9x plus 2 equals 38. Subtract 2, so 9x equals 36. And then divide, which gives me x equals 4. So that would be x. Now, they could ask you all sorts of questions here. They could ask you for the length of one of the bases. They could ask you for the perimeter of the trapezoid. But in this case, we just wanted to solve for x. So next one we're going to look at is this. Very, very similar, right? I know that these are my two bases because these are my parallel sides. And this is going to be my median. So I'm going to average those. So I'm going to take my base 1 and base 2, and I'm going to add those up and divide by 2 because my average, not by 12, is dividing by 2. And then I'm going to set those equal to my mid-segment, which was 5x. So now, combine your like terms, 8x plus 10 divided by 2 equals 5x. And again, this would be a great candidate to divide both of these by 2 and use a Miss Blakely. But if you didn't want to do that, I'm going to multiply by the inverse, right, which is 2 over 1, multiply by 2. And that gives me 8x plus 10, because these both cancel out, equals 10x. So I subtract 8x from both sides. 10 equals 2x, so x would equal 2. Okay, that is it for what I wanted to cover just tonight with segments and angles. That is a smaller topic and one we've been doing since really Unit 1 for the most part, but it's one that we get tripped up on. So we're going to move on to transformations. So if you have any other questions on that topic, I'm going to give you guys about 30 seconds. That would be a great time to send those through. But otherwise, just we'll move on. And I've put on the screen for you guys all of the rules for transformations that we've learned this year. So if you want to take a second and look at those while I wait for questions to come through. Kylie, you can access this later. It'll be on YouTube permanently. And then we'll go from there. And I have a message from Katie. What did Katie say? Katie said, wouldn't the last one be x equals 5? Katie, it totally would. Sometimes when it's late at night on a Sunday, you just forget how to divide. So you are totally right. Thank you for fixing that for me. Perfect. Good. Okay. Any other questions on that? Okay, so this next topic is transformations. This is a huge topic. On the midterm, on the Regents, transformations are really, really important. And a lot of the questions I got from you guys today when I sent you requests was for that. Okay, I had one last question on the trapezoid one. So Margaret asked a good question. Is there any way to solve for that if you're only given one side? So let's say that I was given a trapezoid like this, where they gave me that I wanted that this was X, and they told me this was 14. There is no way with what I know about this trapezoid right now that I could do that. If in words they said something like one base is half of the other, then maybe you could. But given this scenario that you just asked about, Margaret, there's no way I could figure that out. That's too vague because you need something else to average with it. Okay, good question. Okay, so couple things that you guys need to know. For reflections, you will have a scrap graph on the midterm if you need it. You will have a scrap graph on the Regents if you need it. So don't think that you need to memorize all of these rules for reflections, especially given that you know where the x-axis is and know where the y-axis is. Those are ones that I know you can do, right? If you have a point here and you know it needs to flip over the y-axis, well, you're going to know to flip it over to there, right? You guys were wonderful at that this year. So the one that I always say to memorize is this one, because a reflection over y equals x just takes your coordinates and flips them. And that really is something that comes up often. Reflecting over y equals negative x, well, that does the same thing. It just also makes it negative. That's all the negative does. But this would be the one I would say really make sure that you've looked at, because the other ones you can figure out, okay? So point reflections, we have not talked a lot about. A point reflection is the same as rotating 180 degrees. So don't worry about this. I might ask you to rotate 180, but I'm not going to ask you on the midterm to do a point reflection, okay? For a rotation, these are our rotations, okay? These are kind of the four that I could ask you. And when I ask you to do a rotation, I'm not going to ask you in this notation. I'm going to say to you 90 degrees clockwise, 180 degrees counterclockwise. I will tell you about that, okay? But this you can memorize if you would like to, or we can turn our paper and do it that way. I am fine with either. None of this will be given. So some people ask, will these rules be given? They will not. You need to know how to do those. But assume that a rotation is counterclockwise unless they tell you. Okay, those are your rules for those. And then translations, you just move by that amount on your x and move by that amount on your y. And a dilation from the center of rotation, if that's 0, 0, you just multiply by your scale factor, okay? Remember that with translations, rotations, and reflections, these are all rigid motions. Expect that an explanation that you will be writing will require you to use that word, right? We talk about that a lot. But a rigid motion preserves size and preserves shape, right? Angle measure and side lengths. Dilations are not rigid motions. They do preserve angle measure, but they do not preserve length, okay? So a lot of questions I asked were, could we just go over how to do some rotation? So we're going to start with that. So this was one we're going to start with, and I'm going to show you guys using kind of both methods, and I don't care which you prefer, but let's say I like the rule. So the rule for a 180 degree rotation is this. You take xy and you map it to negative x, negative y. So if you have this memorized, great. xy maps to negative x, negative y. So if they tell me that my image or my pre-image is negative 3, 4, then my image is going to map to, well, flip both your signs. So it would be positive 3, negative 4. And that would be your image. Now, let's say we get nervous during a test. We can't remember that. That's fine. So here's what I'm going to do. I'm actually going to do this by graphing. And I need to do this kind of quickly. So I'm going to graph these and put a point at negative 3, 4. Okay? So that coordinate is at negative 3, 4. Whoops, I didn't mean to undo that. Let's undo the whole thing really quick. Okay. So that is my pre-image, right? If I want to rotate this, here's what I'm going to do. I'm going to take this, and it tells me to go 180 degrees. So, does it tell me which direction? Let's see. It doesn't, but for 180, it doesn't matter. So I'm going to go counterclockwise because it tells me positive. So I'm going to rotate, that would be 90, and then this would be 180, okay? And so notice where that lines up. It goes from your second quadrant to your fourth. Now when I look at this point, I didn't actually have points on here, but I could. It's now at negative 3, or at 3, negative 4. And then you could spin your paper back around and graph it there. But this would be where my A prime is. Okay. So I'm going to do a couple more of these just because people requested it. And then we're going to get into some more difficult problems with describing and things like that. 5, 2 is rotated 90 degrees counterclockwise. So let's do it with the rule, and then we'll do it by rotating. So with the rule, 90 degrees counterclockwise would be this rule. So xy is going to map to negative yx. So xy maps to negative yx. Okay? So here's what I'm going to wind up with. My pre-image point was 5, 2. And so that's going to map to negative 2, 5. Switch the order and change the sign of what was y. Okay? Now, the next thing I'm going to do is show you how to do that by turning your paper. So I'm going to graph this point. 1, 2, 3, 4, 5. 1, 2. So that is the point 5, 2. That is my pre-image. I'm going to take that whole thing and I'm going to spin it 90 degrees counterclockwise. And so now look at where that point is. It's at negative 2, 5. So that would be, they didn't give me a name for that, so I can't label it like A prime or anything, but that's what that would be. Okay. All right, so we're going to actually do a little bit of practice with these. So again, as we're going, send me questions, okay? Feel free to send me questions as you're working. But let's do some actual practice with these. So this one says, given the point A, negative 2, 3, state the coordinates of A under the composition of transformations. And on the test, I would put this into words for you, okay? So I'm going to start with that pre-image point. So let's put that on here. So I'm drawing my x and my y-axis, and I'm going to negative 2, 3. So that's my point A. Now, the first thing it's asking me to do here, and again, I would put this in words for you, would be this thing on the right. We read this from right to left. And that is to reflect over the x-axis. So if that's A, I'm going to reflect over the x-axis. Remember that x is horizontal. This point is 3 above the x-axis, 1, 2, 3. So I'm going to go 3 down to graph the image of that point. So A prime would be right here. Then it tells me to translate negative 3, negative 4. So that tells me, remember it's always x and then y. So I'm going to go left 3, down 4. So I'm going to take this and I'm going to go left 1, 2, 3, and then down 1, 2, 3, 4. So that point right there, I would label A double prime. And I am not done. Notice it also says state the coordinates. So I'm going to state them. So A double prime would be at negative 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5, 6, 7. So how do I know to go from A to A prime? So that is, again, what it asked me to do in the problem. it said to reflect over the x-axis. And so that's what I did. I said start from A, reflect over the x-axis, and go to A prime. So I just flipped over. All right, we're going to do another one of these. Let's see. Let's look at this one. So on the accompanying grid, graph and label ABC, and then it says to find A double prime, B double prime, C double prime after a reflection over the line y equals x, and then over a reflection over the x-axis. So we're going to do both, okay? So I'm going to start by graphing my triangle. So 3, 1 will be right here, that's A. 0, 4 will be right here, that's B. And C is at negative 1, 2, 3, 4, 5, 3. So that's C. So this is my pre-image. Okay. The first thing I'm going to do is reflect over y equals x. And this is the one that I said I would try to memorize. What's going to happen with y equals x is your coordinates are going to flip. So A was 3, 1. That means A prime will be at 1, 3. So that is A prime. B was at 0, 4. So that's going to go to 4, 0. So that's B prime. C was at negative 5, 3. So that's going to go to 3, negative 5, 2, 3, 4, 5. So that's C prime. And this is going to be what your image looks like. Okay? It should look like it got reflected over the line y equals x, which goes, which goes like, I'm going to go from the top down, like that kind of. It goes through 0, 0 with a slope of 1. So it should look flipped over that. Okay? Now it wants me to reflect over the x-axis. So B is at 4, 0, or B prime. That's not going to move. So B double prime would be at 4, 0. Okay? A prime here is at 1, 3. So that's going to go to 1, negative 3. So that's A double prime. And C prime is at 3, negative 5. So that's going to go to 3, positive 5. So that's C double prime. Okay? And those would be my coordinates. Be aware that you should follow the order they give you. We will say it in words and just follow the order. If it says blank followed by blank, just realize that. Okay? Okay. A couple people are saying that the audio is a little delayed compared to the video. That's totally normal. It just depends on how fast your internet is running. So just try to make sure you're following along with what I'm doing and what I'm saying. Okay, so let's see. What do I want to do next? It's 7:40. So let's look at this, describing transformations. We're actually going to look at 2 examples first, and then we're going to go from there. Okay, so the first example is straight from the last Regents. This was from August Regents. And it says, these are given. Describe the transformation that occurred. And so I want to look at some that got full credit and some that got not full credit and talk about why. So here is the first full credit one. They said a reflection over the origin, which we would also call a 180-degree rotation, in a translation x minus 1, y plus 1. So notice they said reflection, and they told me what over. And they said a translation, and they said by how much. They were very specific, right? The next one said rotate 180 degrees about this point. And that's fine. That got full credit because they told me a rotation, how much, and about the point. And then the last one that received full credit here was they actually wrote it in this notation. And they said first to do a dilation by a scale factor of -1, which a lot of people wouldn't think of, but this got full credit. And then to translate, and they told me by how much. Those are all great. They're very thorough answers. These did not get full credit. So they said it was translated up 1 unit, it was translated to the left 1 unit, and it was rotated 100 degrees counterclockwise. This was one answer. They were very detailed in what they said, but they did not get full credit because, look at this, they did not state the center of rotation. So when I say to you guys when you're describing, hey, it's important to make sure you're including all of those details, it is, okay? Make sure you include that. What did it rotate around? By how much, right? Because this was on a coordinate plane, they weren't picky about if you said you're mapping. But off a coordinate plane, we would want to have that, okay? So let's look at one like that. This is one off a coordinate plane, and this was from last June's Regents. So it says, these triangles are drawn. Write a sequence of transformations that maps ABC to DEF. The first thing I want to call your attention to, guys, is this, ABC onto DEF. So this is 1, and this is 2. And so we need to be careful of what comes first and what comes second, right? The second one, so let's look at some examples. So this is the first one. They said a translation along vector CF so that C maps to F. So let's look at that. They took a point. They said this would translate up to here. And then my triangle would look like this. So that at least got them touching, okay? And notice how specific. They said along what vector, and they said what it mapped to. Then they said a rotation. They said the center of rotation. And then they said what mapped to what. And so that's important here. So we have this triangle, right? We want to take that, and we want to rotate it, keeping F stationary until those map onto each other. So that's really what I want to see here when I ask for an explanation like this. Okay, that one got full credit. This was another. Rotate ABC clockwise around point C. They gave me my center until the segments were parallel. And then translate along the vector so that we knew what point mapped to what. Okay? So let's actually look at some that wouldn't. This first one said, first you translate to the right. Next you would translate up. Last you would rotate until A matched up with D. This is true, but this is not detailed enough. How much do I translate by, right? How much do I rotate? Around what? We need all that information. That's in there. This is another one. They demonstrated knowledge, but did not write a complete sequence. Translate and rotate. Sure, that's true, but that's not a complete sequence. Okay, so make sure that that's in there. All right, so let's try 2 of these. So this first one says, the graph below shows triangle ABC and its image. Describe a sequence of rigid motions which would map ABC to A double prime, B double prime, C double prime. Notice, 1, 2. I would encourage you guys to label them, to remember, right? The other thing I would encourage you to do is to actually graph on your graph what you're saying happened so we can be sure that that's what happened, okay? So first when I look at this, I'm going to zoom in a little just so we can see. I can tell here clearly that this is going to flip over that line at some point. I don't know whether it happens first or second, but I can tell that it's going to flip. So I know that there's a reflection. So I'm actually going to start by doing that reflection. So C is 2 away from the y-axis, so that's going to map to right there. That will be C prime. B is more than 2 away. Let's see, 2, 3, 4, 5, 6, 7, 8, 9 away. So that's going to map to 9 over on the other side of the y-axis. So that would be B prime. A is 4 away, so that's going to map to 4 away over here. So that would be A prime. So the nice thing about this is now it's going to be easy for me to see what to do next. So the first thing I would say here is 1, I reflect triangle ABC over the y-axis. And that is complete enough because I've said what I'm reflecting over what, right? If you include a mapping there, just make sure those points are labeled on your diagram, okay? Now we need to actually do the second part, which would be to translate it. So I look at this and I see, all right, how did this translate? It went down 2, and I'm looking at corresponding points, right? Each of these corresponding points went down 2. So then I would say, and then translate down 2. And I know here that I'm going to have C prime map to C double prime, right? A prime map to A double prime. Because this is on a coordinate plane, sometimes they're not as picky about it. And so this would get full credit here. It's on a coordinate plane. You described it fully. You didn't need to include the vector there because I have a defined coordinate plane and I know it's down 2 boxes. But if you include the vector A prime, A double prime, or you include the mapping, that's fine. Okay? So that would be my transformation there. Here's what's tricky, and let's look at the next one. A prime, B prime, C prime is given. Describe a sequence of rigid motions that would map ABC onto A prime, B prime, C prime. So, let's think about this. When I look at this, I can see that there was definitely a slide, right? There was definitely some kind of translation. And I'm just going to play with this hypothetically. So let's say that C slid over to C prime here. That would look like this, right? And then what this could do is it could rotate around and map onto there. That's going to be kind of my game plan here, is figure out what it looks like happened and then go from there. So I'm going to first say, okay, it translated from C to C prime. So I'm going to say triangle ABC translates, and here you need to be specific, along vector C, C prime, vector symbol over it. Okay, translates along vector C, C prime. And let's look back at the example one, make sure we're being thorough. Translation along vector whatever CF, so C maps to F. So I'm going to make sure my mapping's in there. So along vector C, C prime until C maps to C prime. And then it's going to rotate, and then rotate. And I'm going to say it goes this way. It goes clockwise, sorry. Clockwise. I don't know the angle, so do not guess an angle. Okay, clockwise, about point C prime until A maps to A prime and B maps to B prime. And that is the kind of response that would get you full credit, okay? I know it's very thorough, but we've been describing transformations like this all year, so I know you guys can do this. Just take your time and make sure you've included every part. Okay. One last one, and then we're going to do a couple proofs, and we'll be done. Okay? Last one. So this says, describe the transformation that was performed. Now, let's look at this here. Let's be aware that a dilation occurred, right? It got smaller. So take a look at this, think what you think. Ooh, I just got a good question on the last one. So last question I got was, would that one work if you reflected instead of rotated? Here's the only difficulty I see with reflection on this one. It would work. But I don't see a clear line of reflection. So you would need to actually construct with your ruler and compass the line of reflection here and construct this until it perfectly mapped. So you can do that, right? But if you reflected it, let's say you did that. I'm just going to erase these for a second. Maybe you reflect this so it goes over some line in the middle of C and C prime, right? So you could construct the line of reflection by connecting those and bisecting it. And A prime would map to over here, and B prime would map to over here. So now you've got this triangle where the orientation is different. And so you're going to have to reflect it again to get the orientation to match up. So I would say if they don't give you a line of reflection and it's not glaringly obvious to you, don't go for that. But if they give you one, then I think go for it. I think that's a good option. But that's a good question. Okay, so last one. It is very clear to me that there was a change in size here, right? So this was a dilation. So let's try to figure out what our scale factor was. So it tells me that I'm going from ABC to A prime, B prime, C prime. So my pre-image, this length was 1, 2, 3, 4, 5, 6. My image, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So it went from 6 to 15. So let's figure out what our scale factor would be, right? My scale factor here from 6 to 15 would be 15 over 6. That's my ratio of the sides. Or I could reduce that. That would be 3 goes into both of those, 5 over 2. Right? Or 2.5. So this is 2.5. Now let's check and see if that's all that happened. The best way to do that is I'm going to pick a point. So let's say I take A. And that's at negative 2, 4. If I multiplied that by 2.5, let's see what I would get. So negative 2, 4. Multiply that by 2.5 would be negative 5. And 4 times 2.5 is 10. Let's see if that's what we got. So negative 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is what we got. So this was a dilation by a factor of 15 over 6, 5 over 2, 2.5, whatever. Okay? And that's not all. So we would say with center either at the origin or 0, 0. That would be my complete description. Now, are these congruent? I could say no, because dilation is not a rigid motion, and thus they are not congruent. Okay, send any questions you have on those. I'm going to briefly go through the theorems we know for proofs, and then I'll answer any questions that we have on those, okay? Okay, so proofs. We have congruence and similarity. Congruence, we have 5 congruence theorems. We have side, 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 angle, side, angle, angle, side, angle, side, angle, and right triangle HL. Okay? The ones that do not work, the no bueno, not our friends, are angle, 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 and angle, side, side. Those are the no-goes, the ones we don't want. Excuse me, right? Those are not good. Okay. For similarity, we have 3. There's really more, but they all come down to 3. We have angle, angle, similarity criteria. We have side, angle, side, similarity criteria. And we have side, 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 similarity criteria. Now, I always get people asking me, what about like angle, angle, side? Well, guess what? That's angle, angle. What about angle, side, angle? Guess what? That's angle, angle. So these are kind of taken care of in that. okay? But again, angle side side does not work. And remember that here we're looking for congruent angles, but proportional sides, right? Not congruent sides. Here, we're looking for congruent angles and sides. Okay, so I have 3 proofs to do, okay? And we're going to go through these relatively quickly, but remember, you can always rewatch this, you can slow it down, and you can send me questions, okay? So first one, you're given that this is a rectangle, and I want to show that I have 2 congruent triangles. So triangle ABD is congruent to triangle BAC. So I am going to look at those and say, okay, what do I know? Well, they give me that this is a rectangle, so that's probably going to be important. So rectangle automatically should make you think rectangle, right? So I know that this angle and this angle are right angles. I know that. So those have to be congruent, okay? In a rectangle, I also know that opposite sides are congruent. And then you have a lot of other things you can use here. You can use the fact that in a rectangle, the diagonals are congruent, and that would give you right triangle HL. Or you can use the fact that that side overlaps in these 2 triangles, so that is reflexive property. So what I would do on this, I'm going to use reflexive property there. So I'm going to say statement and reason. And again, on the midterm, you're going to write your given there. Caroline said, can we bring colors, pencils, or markers? Please bring them. That would be great. Okay? So I'm going to start with my angles. So here's what I know. I know that angle CBA and angle DAB, and you can dab when you write that if you need to, are right angles. Because in a rectangle, we have right angles, all right angles, right? I could put a 4 in there. And then what I know is that that means they must be congruent, because if they are both right angles, then they both must be congruent, because right angles are congruent angles. So my plan here is side angle side. That's the angle part. Now I'm going to find the 2 sides. So step 4, the next thing I marked was the opposite sides, right? CB and DA. So CB is congruent to DA because in a rectangle, opposite sides are congruent. 5, I have this AB thingamajigger. I know that AB is congruent to itself by the reflexive property. If you want to get really fancy, reflexive property of congruence, but reflexive property, right? So that tells me I have all 3 checked off. That allows me to say that the triangles are congruent. So triangle ABD is congruent to triangle BAC by, this is side, angle, side, right? Now, I just got asked a good question. Will it tell you whether it's a congruence or a similarity proof? Well, I knew this was a congruence proof because of that. On the next one, we might not know. So on one like this, it wants me to show that these segments are congruent. So that doesn't tell me to prove that these triangles are congruent, but it tells me to show segments are congruent. And that's only true in congruent triangles, right? In similar triangles, the segments don't have to be congruent. So that's kind of how you're going to know if it doesn't say. It might tell you, but it won't necessarily. So you might need to use some deductive reasoning there. All right, let's do this one. So I know this is a p-gram. I know that E is a midpoint. And I know that FE is congruent, or I want to prove that FE is congruent to GE. So here's what I'm going to start with. Yes, statement reason, but first let's come up with a plan. So it's a parallelogram. That means I have parallel sides. Parallel sides make me think alternate interior angles. Okay? So I'm keeping that in my mind. I know that E is the midpoint of DB. So DB has to be split in half. So those segments are congruent. So my guess would be that I'm looking at these two triangles. And here's how I know that's a good guess. Guess what is in those triangles? FE and GE. Those are sides. So that's how I'm going to know, okay? So what else do I see in these triangles? Well, I have these congruent sides. I see some vertical angles there. And remember, parallelogram, these are parallel. So I see here that I have like a Z, right? These are going to be alternate interior angles. You also have alternate interior angles right here and right there. Those would also work, but I'm not going to use those just because I already got a pair. So, step one given, again, recopy exactly as you see it. Step two, okay. So, I'm going to say, I know E is the midpoint, so my plan here is angle, angle, side. None of those are given in my given. So the first angle I see, let's start with that one, is that, let's call that 1 and that 2. Angle 1 is congruent to angle 2 because, remember, you want your full reason, parallel lines cut by a transversal implies alternate interior angles are congruent. So that's 1. Next, I'm going to label angle 3 here and angle 4 there. Angle 3 is congruent to angle 4 because vertical angles are congruent angles. So that's 2. Now the sides. So I know that's a midpoint. So I'm going to say DE is congruent to BE. And that is because midpoint implies 2 congruent segs. Boom. I've got all 3. So that allows me to say that the triangles are congruent. Okay? Triangles are congruent. So FEB is congruent to GED, which is by angle, angle, side. Notice I didn't prove my proof statement yet, right? I just showed the triangles were congruent. But now I'm going to say, okay, that means that FE is congruent to GE because I know that if the triangles are congruent, their corresponding segments are congruent. So, a question that came through that said, would you need to prove that the lines are congruent? So, I'm going to answer 2 different things on that. Number 1, if you mean the sides of the parallelogram, we do not, because we have all the angles and we have 1 pair of sides. If you mean the sides in the proof statement, then yes, we absolutely do. This right here. But I did that in my final step. Okay. So those are normally our most involved proofs where we have to show the triangles are congruent and then go even further with that. But remember, you know corresponding parts. Okay. All right. Continue to send questions. And we're going to do the last one. So here's my very last proof, and then I'll be out, and you guys can hang around and ask questions if you would like to, or you can go and chill and study for another test tomorrow. So this tells me that these lines are parallel. Cool. And it wants me to prove this thing. I don't see congruence or similarity there, but I see a proportion, and proportion makes me think proportionality, makes me think similarity. Okay? So let's look at what it actually asked me to show. WI over Ooh, did I do this backwards? I did this backwards. This should be WI over WT equals WH over WC. So WI over WT, right, corresponding sides, is WH over WC. So what it's talking about here is showing that this little triangle is similar to this big triangle. Okay, so think about your similarity theorem. I see parallel lines, and I see nothing about side length, so my brain goes to angle. So, parallel lines, the first thing that I see here is I see that if these are parallel, these angles must be congruent because they are corresponding. That's also true about these angles. And lastly, I know that this angle has to be congruent to itself because it is reflexive. It is in both triangles. So I'm going to start my proof. I'm going to do statement reason. I'm going to start with my given, which you're going to copy down exactly, but for the sake of time here, I am not. And I'm going to start with angle W. So angle W is congruent to itself because of reflexive property. It is an angle in both triangles. By reflexive property, it is congruent to itself in both. Okay. Then I have angle 1 and angle 2. Those will be the two I pick. So I'm going to say in my step 3, angle 1 is congruent to angle 2 because parallel lines cut by transversal, you hear this in your sleep now, don't you? Implies corresponding angles are congruent. And guess what? My plan was angle. I have shown both of those. So now I can say, okay, cool. That means triangle WIH is similar to triangle WTC by angle similarity. Or your teacher might have you write out two corresponding angles congruent in triangles implies triangles are similar. Okay. Now I can get to my proof statement. So step 5, I can say this first one, which is WI over WT equals WH over WC. The reason being the triangles are similar implies corresponding sides are proportional. And if we wanted to go one step further, and again, this is about the hardest that these similarity proofs will get in asking you to prove things, would be, okay, well, guess what? I could cross multiply this and get WH times WT and WI times WC. So WI times WC equals WH times WT. And this then says, okay, well, what's the way we say that? Doesn't say it. Our reason, why do we always say that, is to say, okay, we cross multiplied. We would say the product or a proportion implies the product of the means equals the product of the extremes. And again, that's like the hardest you're going to see with these is, as far as like things to prove, is trying to get the proportion and then to that cross product. Okay, I see a couple questions, so keep sending them. I'm going to answer what I can right now. Question, is there a curve on the midterm? That entirely depends on scores. So the way that curves typically work is teachers look at what the scores are and if a curve is warranted or not. Last year, I don't remember. So that's going to be dependent on how the tests go. I would imagine there won't be a huge one. I think it's a very fair test. So I would just make sure you're prepared and don't stress about a curve. But if there is one there, it just helps you. Do you always do proportions in a similarity proof? No. Sometimes you're just showing the triangles are similar. In this one, it happened to ask us for the proportion. Okay. Will there be constructions? Yes, there are. There is one actual construction and a multiple choice on a construction. So, like asking about a construction. Tomorrow night in my review, we're going to do some constructing, but just study ones that your teachers have reviewed. The one on the midterm is not a crazy one. It is one that I think is very fair. What does product of the mean equals product of the extreme means? Good question. Okay, so let's look at this. In a proportion, you guys know to cross multiply, right? Top times bottom, top times bottom. So we have fancy vocab for things in math. You guys know this. So the mean in math typically means the middle, right? So in a proportion, think about, normally I'd write this over this equals this over this. That's kind of the order I write them in. So we call the two things you write in the middle the means. And then the extremes are like the first and last. So this is an extreme. And this is an extreme. And so it's kind of like how extreme temperatures are highs and lows. First and last are extremes. So product of the mean equals product of the extreme has to do with that when you cross multiply, you are multiplying the means by the extremes. And so you're just cross multiplying those. It's a fancy way to say cross multiply, but that's the, proof reason that you might put that. Good question. Okay. Everything that I had planned for tonight is done. So big ups to the 10 of you that stayed out this whole time. I hope that you learned something that could be helpful, or at least got practice with something that could be helpful. I'm going to stay for about 5 more minutes and take questions. So I'm just going to sit here awkwardly until you guys send me questions. Don't be afraid to ask. I don't have to say your name, but your question might be what somebody else is thinking. So thank you for asking them. So please send away whatever you guys have for questions. And if not, feel free to sign out, and we'll do this again tomorrow. And until then, I'm just going to show you guys this turtle. This is my turtle. He hangs out on my desk. He holds string. Okay, will the review be at 7 again tomorrow? Yes, it will. And same idea, I will have a link up. I'll send it out on Remind. Send questions the same way. What else? What else? I will also put this key up on my website, so you'll have the whole filled-in key to all the problems I just did. I'm giving you guys 2 more minutes, and then I'm going to watch football. Okay, I think we're good. All right, have a good night, guys. Thank you for sticking with me. I hope that you got something out of it, and I will see you guys tomorrow night. Bye.